So probability density, psi squared is the probability density, the probability of finding an electron at a given point in space. So we could express that as the probability divided by the unit volume. So an s orbital is spherical. That's kind of convenient. S and spherical starts with S. So what we see there is that the probability density decreases as the distance from the nucleus increases. So we can look at a plot of this, and it resembles a multiple exposure photograph. So you can take a picture, and you see all the electrons there. Take another picture, electrons over here. Take another picture, electrons over here. That's what it looks like. It's important to understand that the electron is not moving around the nucleus like a moth around a flame. Sometimes think of it that way, you know, it's a squirrely little particle and it's just in this area, we don't know where it is. But it is not actually like that. In a sense, the electron is spread out over the entire volume. That's a little bit hard to understand. But remember, electron can behave like a wave and a particle. And a wave can occupy a large volume at the same time, even though it's not actually a thing, right? It's kind of confusing. So if we look at the probability density, here would be the multiple exposure type photograph, where each of these dots would represent the electron at a certain point in time. And so if we take lots and lots of these snapshots, we see that in this sphere is where the electron is most of the time. And it's more dense in here, and it gets fuzzy at the edge. But a plot like this is misleading, because if you graph the probability density versus the radius, you see that the highest probability is at the nucleus. And then it falls off out as you move away. So that suggests that the electron is most likely to be found at the nucleus. But we know that the electron is not at the nucleus. So probability function didn't quite work. So the radial distribution function is what seems to work a little better. So this is the total probability of finding an electron within a thin spherical shell at a distance r from the nucleus. And this gives us a better idea of where the electron is likely to be found. So this is the probability divided by the unit volume, that same thing we were looking at, times the volume of the shell at that distance r. So when we put these two together, we've got opposite trends. So the probability over unit volume was largest at the nucleus, but when we multiply by the volume of a shell at the nucleus, that's going to be smallest at the nucleus. In fact, it would be 0. And as you move out, it gets larger. So we have opposite trends in these functions. So we look at a graph of the radial distribution probability, and we see that it's 0 at the nucleus. It goes up quite steeply, hits a maximum, and then goes back down. We have this maximum probability at 52.9 picometers for a hydrogen atom. And that says that the 52.9 picometers is the most likely distance for an electron to be found from the nucleus. This is the same radius that Bohr predicted from his calculations. And so these two ideas agree, but there's an important conceptual difference. In the Bohr model, the atom is like the solar system, and so we have the electron going in a circular orbit around the nucleus, and Bohr calculated that and said that it is 52.9 picometers from the nucleus. But quantum mechanics says that the electron is found at multiple radii from the nucleus, but the most probable is 52.9. So there's an important difference there. Does anybody have any questions yet? This is all kind of weird stuff. Yeah. This graph is just for the helium atom. For other atoms and for other electrons, this would be the 1s electron for a hydrogen atom, that maximum would be different. It would be a different distance. So that was a 1s orbital. 2s and 3s orbitals are also spherical. They're going to be larger than the 1s orbital, and they're going to contain at least one node. So a node is a point where a wave function goes through zero. So if you take a piece of string or a piece of rope and you wiggle it, you can set up a standing wave. And that's what's going on here. Standing wave. And what we'll see is that there are points that appear to not move. And those are called nodes. And so this is a lot like what an electron is doing. The orbital is like a standing wave for the electron. But it's not two-dimensional like a rope in a standing wave would be. When we look at this standing wave, and I'll show you a video of one in just a minute, it appears that the rope is everywhere in this little football-shaped area, right? Because it's moving up and down. Now, is it everywhere at the same time? Well, yes and no. If you take a picture of it, you would see that it is only in one place, but it appears to be everywhere. Okay, let's try to find that video. So in that video, we saw the string moving, and it's blurry here, so it looks like it's filling that whole space, doesn't it? But we know that it's just a string moving. And so it's a little bit like, it's the best illustration I've got for what the electron's doing. The electron is a particle, but it also behaves like a wave. And its wave nature is how it can seem to be occupying this entire spherical volume, when actually it's, if you would take a picture of it, you would find it at a specific point, because that collapses those two states, and it has to be one or the other, a wave or a particle. Any questions? So the 2s and the 3s orbitals, also spherical, but they're like the higher harmonics of the wave on the string. And so now they have nodes. So the 2s orbital has one node, and the 3s orbital has three nodes. A node is just a point where that wave function goes through zero. So there's zero probability of finding the electron there, which seems kind of weird. It's a particle. How can it be on this side and on that side? But we saw with the string can do it, right? The wave is here and here, but there's no waving going on right there at the node. So here's the 2s and the 3s orbital. So they're both spherical. If you just look at them from the outside, they just look larger than the 1s. But the 2s orbital has a node here where there's this sphere in the middle where the electron is not. And if we look at the radial probability distribution, we see that there's a small maximum here, and then there's a node, and then it goes up again. The 3s orbital has two nodes, and so we've got this little one, and then a bigger one, and then a bigger one. That make sense? Kind of? So the 1s orbital, each principal energy level has an s orbital. And so there's a 1s, a 2s, a 3s, etc. It's going to be the lowest energy orbital in that given principal energy state. They're spherical, and the nodes number of nodes corresponds to the principal energy level minus 1. So the 1s orbital, 1 minus 1 is 0, no nodes. The 4s orbital, 4 minus 1, that would have 3 nodes. Okay? The p orbital. So this is where L equals 1. Our quantum numbers, n equals 1. The only possibility is L equals 0. And L equals 0 corresponds to S. You get to the 2, 3, 4, principal level, you can have a p orbital, and that's where quantum number L is equal to 1. So when L equals 1, M sub L could have 3 different values, -1, 0, and +1. So there are 3 different p orbitals. And what's different about them is their orientation. So they're aligned along different axes. So 3-dimensional space, we've got an x-axis, a y-axis, and then a z-axis. And so these are lined up on those axes. The p orbitals are 2-lobed, so they have one node at the nucleus, and then as you get larger and larger, they also have additional nodes, somewhat like the s orbital did. So here's the radial probability. As we go distance along a lobe from the nucleus, it rises up and goes back down. So that's moving from the nucleus here at the origin and going out. And this blurry thing here corresponds to this increased probability. So there's an increased probability on one side along that x-axis and along the other side. So these are the 2 lobes of that p orbital. So this is the more multiple exposure photograph, and then this is representing it more as a solid object, which is much easier to draw. But it's important to understand and remember that this is not a container that the electron is found in. This is just a representation of the space. So there's the px, the py, and the pz. They look a lot like dumbbells or balloons tied together. Any questions? When L equals 2, those are the d orbitals. And then M sub L can have 5 different values. So there are 5 d orbitals. 4 of these orbitals are aligned in different planes, and the 5th is aligned along the z-axis. Most of these, well, 4 of them are 4-lobed, and one is really a weird shape. It's a 2-lobed thing with a toroid. These have planar nodes, and when you get to higher principal levels, you also have spherical lobes. So we looked at the nodes in the s orbitals, and that was tricky enough. We're not going to look at the details of these, but they do have nodes. It's just a lot more complicated. So those are the shapes of the d orbitals. So it kind of looks like a double p orbital, right? So it's got 4 lobes, and so there's this one, that one, that one, that one. Those are aligned in different planes, and then the 5th one is really weird. It looks like a p orbital with a ring around the middle, like a kid going swimming in one of those lifesaver things. Any questions? F orbitals, when L equals 3. L equals 3, now we've got 7 different values for M sub L, so there are 7 F orbitals. These are even crazier shapes. Looks like balloon art gone insane, right? So we've got these guys that are sort of similar. They've got 8 lobes, and then we've got these guys, 2 lobes, 2 toroids, and this big node at the nucleus. I do not expect you to remember the shapes of the F orbitals. I would be hard-pressed to draw those myself. So the orbitals are mathematical wave functions. So we can think of them as standing waves, like the wave on the string, except these are 3-dimensional and they've got some rather fantastic shapes. But just like the wave on the string, the wave function for an electron can have a positive value or a negative value. And so that would correspond to being above the midpoint or below the midpoint. And then you can also have nodes where the wave function is equal to 0. So the sign of the wave function, whether it's positive or negative, is called the phase of the wave. When orbitals interact, their wave functions interact as well. and they interact like waves do. We saw the constructive-destructive interference when we talked about the nature of waves. These are also wave functions, and they can constructively and destructively interfere with each other. So if the functions are in the same phase, the same sign, then they are considered to be in phase. If the wave functions interacting are of opposite sign, then they're out of phase, and they're going to interact destructively. And that becomes very important when we talk about bonding, but that's in a different chapter. Any questions? Here's illustrations. If we think of the wave on the string, so here the s orbital would correspond to this. It's all going to be either positive or negative. And the p orbital has a node in the middle, so one side is positive and one side is negative. So it has two phases. And so depending on how you line them up, you get them to interact differently. So we looked at all these crazy shapes, right? This is where the electrons are, and the electrons are what's occupying most of the space of the atom. And yet we've been drawing atoms as spheres, right? We depict atoms as spheres because they are spherical. When we superimpose all of those different orbitals, we get a roughly spherical shape. So atoms are not hard little marbles, although it's convenient to think of them that way. But rather they're a collection of these fantastic wave function shapes. But all of those combined together give us overall a spherical shape. Any questions?